Hi everyone, I'm Gabriela Albazabala and I'm an intern here at Emerald Digital. I'm really happy to be here, and today I'm going to walk you through how the neural networks have evolved throughout the years, okay? So we're going to start with the very first neural networks all the way to the transformers, and not the ones from the movie, the ones from, they're actually the models behind ChatGPT, Gemini, Bird, and many other AI tools that we use every single day. We'll take it step by step, so don't worry. And we're going to start with the perceptron, which is the simplest type of neural network. And then we're going to talk about the architectures that we have right now, which are the ones that can understand and generate human language today. So the agenda for today, I'm going to give you a little bit of an introduction. Then I'm going to talk about the perceptron, the multi-layer perceptron, the deep neural networks, convolutional neural networks, the recurrent neural networks, and the transformers. Specifically in the transformers topic, I'm going to talk about the attention mechanism, which is the core of the transformers, and then the tokenization and embeddings, also the encoder and decoder, which is the architecture, and the positional encoding. Then I'm going to have some time to do some programming, where I'm going to show you how to do some applications with the transformers. Then I'm going to talk about the limitations, because not everything is sunshine. Actually, we have some problems or limitations with the transformers. And then I'm going to have a section with questions and answers. Okay, so even if you don't realize it, you use AI and transformers every single day. For example, I bet that you use ChatGPT to ask him questions about something that you have any doubt. And another example is Google Translator to search the meaning of a word in another language. Or another example is even YouTube auto-generates subtitles, so that's another example. All of those three examples, the transformers are working behind the scenes. So, okay, they are working behind the scenes. So let's start with the perceptron. The perceptron, it takes like several inputs, like you can see in the image. It has a function activation, and it has like neurons also. And you can see here the visual representation of the perceptron. Okay, so it was created in the 1950s, okay? And you can say that it's the ancestor of the modern neural networks today. It takes several inputs, multiplies them by weights, and then sums them up and applies an activation function, and then returns an output. Then the perceptron has some problems, as I'm going to say next. But first, I'm going to give you an example. Okay, so let's imagine that you want to decide if an email is spam or not. Okay, so the perceptron learns based on simple rules and learns to classify, but only with data that's linearly separable. As you can see in the image here at the bottom of the slide, you can see that we have two types of classes. So that type of problems are the ones the perceptron it's more familiar with. Okay, then the multi-layer perceptron. This one overcomes actually the problem that the perceptron has. For example, this one has one or more layers, and also, as you can see here, has more neurons. This one can learn more complex patterns, and it's like, and the key idea of this type of neural network basically is the backpropagation, because maybe you are wondering what's the backpropagation, and the backpropagation is like the network updates the weights automatically, and then, however, this is based on its mistakes. Then we have the deep neural networks. These ones, they appeared because they started adding more layers and more layers to the neural networks. These became really great at resolving complex tasks. However, they required a lot of data. The training was very slow. So that's like one problem of this kind of neural networks. So this one is, they had bigger models, better learning, but more data and compute needed. And then we have the convolutional networks. This one, instead of connecting every neuron to every other neuron, this one uses something called filters. The filters scan over one part of the image, like for example, features or shapes or edges. And so these convolutional neural networks became really good at computer visional tasks, like detecting dogs, faces, cats, and many other things that you can imagine. But however, these neural networks weren't designed for sequential data like text or audio. Then the recurrent neural networks, they are really good at sequential data. For example, they take step by step the words of a sequence, and so they are very good at text and speech. So now the networks have memory and they understand sequences, but you need to remember that these kind of networks, they have some serious problems, and why we needed something else. As I said before, the recurrent neural networks, they were good and everything, but they weren't good at long sequences. So let's imagine that you are reading a book, the page of a book, and by the time that you're finished reading it, you don't remember the first words. And I bet that you don't remember the first word that I said in this live stream. So that was a big problem for the recurrent neural networks, the one that I mentioned here, and also that they can be parallelized easily. For example, they needed to read word by word in a text to understand the context and So that was a big problem to this type of neural network. So the transformers became a really good thing because in 2017, 8 Googlers, they published a paper with the name of Attention is All You Need. And you might think that they were received really well in Google, but they weren't actually. In Google, at big enterprises like Google, they are a little bit reluctant to changes. So they didn't want to change the way they work. So they had to leave the company. And then in 2019, Sam Altman, the CEO of OpenAI, saw the potential in this paper and he created ChatGPT. Okay, so now I'm gonna talk about the architecture of the transformers, which is the encoder and the decoder. The part on the left is the encoder and the part on the right is the decoder. And let's say that the encoder is the one that understands the text, and the decoder is the one that generates the text. And this was the core idea of the attention is all you need. Then the tokenization and embeddings is something that the transformers use. Tokenization means breaking down a text in parts. For example, we have here, the cat chased the mouse. So tokenize that sequence is like breaking down. For example, we have first the, then cat, then chased, then the in mouse. And those words then are converted into numbers. For example, you can see the token IDs, and then those numbers are converted into vectors. Those vectors are the ones that you see on the right, and this process is called embedding of the words. Here in the image at the bottom of the slide, you can see that when you tokenize and embed the words, you have, for example, the vehicles, aerospatial vehicles on the right and animals on the left. So the vectors are here are associated with the ones are more similar with. Then we have positional encoding. So the transformers, they look all the text at once. They don't make the mistake the recurrent neural networks do, which is that they take like every word at a time. No, the transformers, they don't do that. They look everything at once. And for that, the researchers suggested to use the mix of functions like sine, cosine functions, both of them, with different frequencies and different offsets, so every word can have like different positions and can be better recognizable for the transformers. So we can see here that we have the word vector, the positional encoding, the word vector. The positional encoding tells us where the word is, and the embedding with the positional context. And you can see examples of the waves of how they look, of how they kind of look. Then we have the attention mechanism. This is the most important part that I'm gonna talk today in this live stream, because it's the core of the transformers. Okay, so and the transformers, what they try to do is they take every word and try to see how compatible are to other words. They try to see those combinations, and for that they use different vectors. Aquí, here here we have the query vector, the key vector, and the value vector. The key vector represents the word. For example, imagine that a word is saying something like, I am a subject, I am a verb, and the query vector is trying to say what the word is looking for. Maybe that word is looking for words related to nature, or is looking for a verb or a noun. So that's what basically those vectors represent, the ones that we have here, K and Q. In the attention mechanism, we multiply them both. We make a dot product of those vectors, and the result tells us how compatible the words are. It's like if we're trying to see if a key fits in a lock. And with the attention scores, we can actually do an attention matrix like the one that we see at the bottom. For example, we have the word, I'm not going to try to pronounce the word, but the one that I'm putting my mouse on, it's this word, and we see that it has different colors. The brighter the color is the one that it's going to pay most attention to. For example, this word, it's going to pay more attention to the word European. La, it's going to pay more attention to the word de. And so we have here like a matrix of the attention scores. Then we have another vector that we see here a B vector, which means value, are the value vectors. The value vectors represent the useful information the models are going to actually mix and pass on. These values, with these values, we do a weighted sum of these values, and then in this operation, we use the attention scores that we previously obtained. So let's say that at the end of the attention mechanism, what we have is, for every word that we have, a combination of that word with the most relevant words. So that's like the important part of the transformers. Okay, so now I'm gonna show you a little bit of an example. I'm gonna code something. For that, if you want to do what I'm gonna do here, you need to do pip install transformers torch. I already have this installation, so I'm not gonna execute it. But if you want, you just need to press enter. Okay, so the first example, we're gonna use the library with the name transformers by Hugging Face. Okay, so I'm now gonna use it. And in this code, I'm gonna do an example of a summarization with transformers. So now you need to write from transformers, import pipeline. Then we're gonna use another variable with the name. I'm gonna do an application of summarization. So I'm gonna print a title, summarization. And here we're gonna have a variable with the name summarizer. We're gonna use the function pipeline, and we're gonna specify to this function that we're gonna do a summarization. Then we're gonna add some text, the one that we want to summarize from. I have a text already in here, so I'm just gonna copy the text. I'm gonna paste it. Okay, now we're gonna apply now the summarizer to our text. Summary, we're gonna have a variable with the name summary equal to summarizer text max length of 130, min length of 30. Okay, now I'm gonna print the original text. To see the comparison between both of them. And I'm gonna print the summarized text. So now we're gonna execute this code with Python transformers.py. Transformers. And let's see what it's gonna return. I'm gonna try to execute it again. Okay, this should give us, I don't know why it's taking so long. Okay, now it's reacting. This should give us the original text, which is this one. As you can see, this is all the original text. And the summarized text is this one that we have in here. These 3 lines is the summarized text, and I'm gonna show you another one. I hope that you can see it. I'm gonna give you another application, another example of an application of the transformers. Okay. Now we're gonna do a sentiment analysis. And for that, we're gonna save in this variable the classifier equal to the pipeline. And we're gonna specify to this function that it's gonna be a sentiment analysis. Sentiment. And in here, we're gonna have a list with different texts. For example, I'm gonna write something like, I hate mangoes. Another text that I'm gonna write is, I really like the music from, I don't know, Arctic Monkeys. And finally, just for this example, I'm gonna add another text. I wish I could go to Paris. Okay, so now we're gonna use a for cycle. So we can go all over this list. We're gonna save the result in this variable, and we're gonna use our classifier. And we're gonna print like the result. What the transformers is going to do is it's going to classify if my text in here is positive or if it's negative. So it's supposed to say, for example, in here that this phrase is negative, this one positive, and the last one negative. But we're gonna print our result first before we execute it. Result. I don't have in my keyboard this one, so I'm just gonna copy it. Result and an arrow. Result and the label. And here I'm gonna print the text. Okay, I'm gonna change it. I'm gonna print also the score. The score tells us how sure the transformer is of his response. So I'm just gonna try to execute it. Okay, so we have our three phrases here. The I hate mangoes gives us negative, and it's 99% sure that it's negative. I really like the music from Arctic Monkeys. It's positive with 99%, and I wish I could go to Paris, negative 99%, as I predicted myself. So this is everything from my coding examples. I'm going to tell you about the limitations of the transformers. And this type of neural networks, they use actually very, as you can imagine, a lot of computer power. They also need a lot of energy and require a lot of data so it can be trained. Can you imagine that in ChatGPT you need to have like billions of parameters so you can train the model? So that's like a lot. And another one is that you probably think that this kind of technology understands what it's doing, but they are not. They are only recognizing patterns in data. And basically it's like only linear algebra. So it's not like the machine is actually thinking and making decisions with like a human brain does. It's like actually different. So that's everything. If you want to ask something, feel free to ask if you have any question. Juan Manuel Ruiz Aranda asked, why is going to Paris negative? And my phrase was, I wish I could go to Paris. Like my interpretation is that I'm actually sad because I'm not there. So that's why it's negative. Faustino Neri asks if he is going to lose his job soon. I hope that he doesn't. I can't answer that. Maybe you could ask a transformer and see what the transformer answers to that. Another question, where we can find more examples and documentation of transformers and the library you use. You can read the paper, Attention is All You Need. This was the first paper about the transformers, and you can understand more with more detail what the transformers are. And you can also visit Hugging Face. Hugging Face, it's a really good page where you can find Python libraries where you can implement the transformers. So I don't have any more questions, so that's gonna be everything for this live stream. I hope that you can understand a little bit more about transformers and concepts. These concepts that I gave were very fundamental and basic, and I tried to explain it as simple as possible. And that's everything. I hope you enjoyed this live stream.